Everyone, December 22nd. Alright, so today's goal first is we're gonna deal with this, and then we're gonna go through the previous problem again, and we solved it. Last night spent an hour and a half, so we are going to read through the solution and see what, if any, better solutions are out there. And I will go through my solution again, which is I'm pretty proud of it, okay? But we'll have to go through the solutions. All right, let's do today's first. Yeah, this is today. I think it's an old problem. We've done it before. Minimum number of operations to sort a binary tree by level. You are given a root of a binary tree with unique values. In one operation, you can choose any two nodes at the same level and swap their values. Return the minimum number of operations needed to make the values at each level sorted in a strictly increasing order. The level of a node is the number of edges along the path between it and the root node. So what we want to do is you can choose any two nodes at the same level and swap their values. Return the minimal number of operations needed to make the values at each level sorted. So in this case, this requires 1. This requires so 5 need to go to the front, right? So basically you can just go left to right. You know, you find the okay, so you do one swap, you get the 5 to the front, right? And you get, so 2, right? 2. Swap 7 and 5. The third level becomes a swap 8 and 7. So we have 3 operations. I mean, essentially it's just asking for each level what's the minimum number of swaps to make it into sorted order. What is, so from 5, 6, 8, 7. Alright, 5, 6, I should know. The original is 7, 7, 6, 8, 5. How many swaps do we need to make it into a sorted order? So sorted order is 5, 6, 7, 8. So the one that's equal we don't swap, right? And now we find, okay, it's supposed to be 5, but it's 7. So I say, okay, I'll swap with 5. Okay. So now 7 will come here, and now we have 7 and 8, so we swap them. So is it true that we just, do this type of thing and then we can get the correct answer? So in this case, we have 7, 6, 5, and 4, right? So it should be 4, 5, 6, 7. So okay, I'll swap with 4. How do you know where 4 is? It's a good question. Where do you know it's 4? So basically you can say, okay, I'll swap with 4. Right, so we get 4. And then you 6 can be solved with 5. So we have 5. Right? And then 5. Yeah, you already got swapped. And 4 you already saw, so it's also 2. So basically we'll compare, right? If it's, so it has to swap regardless, right? Right, so you need to swap, so it has to be 4 here, so you definitely look for 4. Right, 4 swap here. Okay, so 7 is just go somewhere. So 7 swapped out, right? So you have 4, and then you have a 6. So you say you have a 5, so you swap 5 here, right? Swap 5 here, and then 6 goes out, right? And then you have a 5. 5 is swapped here, so this is actually empty, right? It's empty. So if it's an empty, you can put anybody here, right? You can put anybody here. because 5 got swap out and then swap with 6, so 6 goes in, right? 6 comes in here. Now the thing is, it doesn't really matter, does it? Because you move 4. Oh, this is actually probably not a good example. So yeah, you need to find some value, right? You can swap with the current. That's like a one swap. And then for the next one, it needs to swap as well. So you find the one that can make the swap. Okay, so those just go there. And then eventually, so basically the idea is, will it be a scheme that make the swap more economical, right? Minimal number of swaps to make it sorted. I would like to say it's, yeah, because it's deterministic, right? It's deterministic because you have the smallest that's not in the right position, so it's deterministic that this has to go there, right? You have to swap it there, and once you swap it there, and then this has to come here, right? And then you have deterministically, you have something that has to go to the second biggest, so you have to swap them, right? You have to swap them, and you go to the next one. Deterministically, it has to be this, and if it's not, then you have to swap, right? Even if that value is, so basically you just keep swapping, right? Keep swapping, and then and but how do you code this? It's like the worry is, when you do these swaps, and then after you swap, they're not really sorted. So for example, if I have 6, 4, and 5, right? So when you swap first, then you swap second, then you have to swap again, right? You have to swap again. Let's try, and so my idea is for the second one to not be 6, but be 4 and 5. So I say this shall be giving me 4, right? This is 4. So we just swap them. We have to swap. There's no other way. So now, since this is, so we could probably have an array, right? We have an array to mark which index it is. Okay, so we say at 4, 5, 6, 7, right? The index of 4 is 2, is 3, that's 1, that's a 0, right? So this is a start, and then we have this, right? We have this. We can sort it, and actually it's fine, right? We should just sort it. And once we sort these values, I go to here and I see it's a 2. It's at position 2, but it should be position 0. So I need to go for position 0 to see what is at position 0. Hold a second, I have the original. Okay, I have this, right? And I go through both. I go original is 7, it's a position 0, and then 4. So now we're gonna swap, right? So it should be 4, which is at position 2, so we have to swap with position 2, right? So yeah, so I just need to know which position, right? We swap, and I go to the next one, and it's supposed to be this value, which is at position 3, So you swap, right? So it'll be 4, this will be 7, this will be 5, this will be 6. Now at 7 we find out that, oh, we update its position as well. We update its position, and at this position it should be 6. And we say, oh, 6 is here, so we just do a swap. Right, we do a swap and we count how many, and we can go through the whole thing. And okay, yeah, that definitely will work, but I wonder, serious wonder if there's a better way to do this, because we need to build original and then we have to sort it. Right, we have to sort it. Okay, let's just get this one done. Okay, so what we're gonna do is we need a vector, right? Vector of 3 node. I'm not sure, is that Q? Okay, I think it is. Right, and that's Q dot push back root. Okay, so while Q dot empty, and we have a vector, same thing, temp. Well, we will first compute the number of swaps. Rest plus equal to number of get swap count. Okay, we'll put Q in there. Okay, once we get it, and then we say for auto node of Q, if node left not equal to no pointer, oh, we probably don't even need that if I use a deck. Yeah, I'll use a deck. We do that. Don't need this. Give us size. Okay. And then we say auto node equal to Q dot pop front. Right, and then we say Q dot push back node left if node right. All right. Okay. Oh shoot. Front. Okay. Right, so we just go through every one, get to the next one, and then we keep going, and then at the end we simply return rest. Alright, so now all we need to do is to get the swap. Right, we call it, I don't know, private int get swap count deck. Review this row. Okay. Then we shall say std vector int vals auto node of row vals dot pushback node dot val. Alright, and then we shall say std vector int sorted vals vals dot begin vals dot end, and then std sorted vals dot begin sorted. Sorted files dot end. Okay, so after we sort, we can say we also need the if it's equal we don't swap, right? If they're not equal then we'll swap. So once we swap, we don't know where this value gets swapped to, right? So we need the positions. Oh, positions. Maybe I can do positions. $10,000. Right, 1, 2, 3, 4, 5. Okay, and now we can say position right, so we go through them, we update the positions, and now we gotta sort it. Okay, now we gotta sort it. Then we say int with reset I equals 0 smaller than vals dot size, right? I plus plus. So now we have the 2, so we just need to know where it has to be. So we have the position, so we say p val, right? P val is vals I, p sorted val is sorted vals, right? I have these two, and then we need to know where they should be. Right, we say if positions. So positions PV is not equal to positions PSV. Right? Then we say positions, so into temp is equal to positions PV. Right, and then we say positions, so PV's position will equal to PSV's position, and PSV's position will equal to temp. Right, so we do the swap, and after we swap this one, we do this, and then we need to put them into the position that they should be. So basically vowels, vowels, vowels I, right, vowels I shall equal to PSV, and vowels okay, that we swap them. So PV, the position is this, right? So it's sorted by position. What does P stands for? I don't know what P stands for. You can just say vowel, right? Vowels is this, and sort of vowel is this, right? I swap them, by swapping their positions, and then you say it's, yeah, hold on, I don't know why I say this. It should be like just this, right? If the two positions are not the same, so I swap their positions, and then this I just say position V, right, shall equal to V, and position sorted value shall equal to sorted value. Yep, and then you move on. You go through the whole thing, right? You go through the whole thing. If they're the same, then you don't. If they're not the same, you do a swap. And once it's done, you will return result. Then, yeah, what do you think? It feels very janky. Okay, looks to be right. Let's just give it a shot. 2471 BFS, and for each level we find the minimum number of swaps to sort its values, and the minimum number of swaps is the exact number, is equivalent to the number of swaps needed to get the minimum number of swaps. Simply go down, right, go through the level and swap whenever needed, and swap whenever needed. So I'll say it's ON. I mean, yeah, we go through everybody, and then we go through everybody and go through everybody again. Yeah, I think it's just ON.
There was way too much that came back on the first search warrant for us to think that we were just looking for a dropped piece.
All right, we'll do one more time.
Boys, we might be dealing with a lot more than we think,
We'll try it.
and we have no idea where it's gonna end.
Yeah, I think that is the solution. Nothing too special.
But naturally, some of the first paths that we took were to try to interview some of the people that were released.
So I'm curious if there's any better solution than this hash map. Oh, Owen login. I kept forgetting. Yes, it's Owen login. I kept forgetting because, oh my goodness, I kept forgetting you have a sort.
We probably wanted to get down to the crawl space.
Gaming swaps. You have the original. You have the sorted. You have ordered. Get its positions. Go through. If it's not the same, you will swap, and you swap the positions.
They should be surveilling him.
They went to Casey's house. Casey invited them in.
Oh, there's a function called swap.
Police officers were delighted not only to go to a warmer place, but to go to the house where Casey lived.
They talked with him. John will talk your ear off. And one officer said he wanted to.
Bit manipulation. Oh, isn't this what we're trying to do?
He excused himself to go to the bathroom, which is in the older part of the house. When he was in the bathroom, the heat kicked on, and this odor came up from the heat vents.
He equated it to the smell that he would smell in the morgue.
If you've ever been to a morgue around a dead body, it's an odor.
That's true. Three data still have a position. We have the original vector. We have the sorted vector. We have three.
I smell dead.
Exactly, we have three.
We now were coming to the absolute conclusion that this guy had to be stopped. We needed to get a second search warrant to get back into Casey's house.
You can't just start ripping apart someone's crawl space because of a bad odor. You need judicial approval, so you have to get a warrant. The problem with getting a warrant is you have to connect John Wayne and Casey to rob a piece on the night.
You can combine the node's values and its position into a single number using bit manipulation. Values won't exceed 2 to 20. 20 bits are enough. So you have some bits to store the position and some bits. Okay.
As the evidence was building up against Casey, it became clear that he was starting to feel the heat.
He really started to see the meter change quite a bit.
A 40-bit long integer is technically enough to store both the value and position of a node, where the high 20 bits store the value and the low 20 bits store the original position. Let's see how the... So it's a different encoding. It's fine. I mean, we can always figure this out, right? You have the top, this is your value, and this is your position. It's totally fine, right? What's the purpose of this? So this is your map. So you don't have a, you still need two, right? You need the sorted and the original, and just every time you change, you can change the...
I have to tell you something. Like, okay, John, it better be important, better be new, because you're telling me the same old crap all the time. I want to hear it. No, something important I have to talk to you about. He comes into the office and I'm getting pissed because he's telling me the same old stuff you've been telling me. I lost it. And I start pounding my hand. I'm just pounding it really hard. I says, John, tell me the truth.
Wait, hold on. What the hell?
He goes, okay, do you have anything to drink?
Okay, I understand this part.
And I had it in my car. I ran out to the car, and my old model basically says,
Nodes. What the hell is
close
nodes?
it, basically, right? Fill it up again.
What the hell is nodes? Oh, node is this. Node?
Chair shut. And
A nodes.
he says, I want to tell you the whole story.
Oh, nodes is a vector.
I've been a judge, jury, and executioner
Okay.
for many, many people.
The queue is already ready, right? Because I pushed the queue. So we sort the nodes. Ah, as you sort the nodes, you already... Okay, you already have the correct index along with it.
Meanwhile, across town, cops had a big breakthrough. They
So you get the original position.
photo receipt they found in Gacy's
Uh-huh.
garage.
If original position is not equal to,
She happened to be a
then you need to swap.
at Nissan Pharmacy.
And the story behind that was Kim Byers was gonna go out and take a break, and she asked Rob if she could borrow his coat.
Wait, hold a second. Swap nodes.
Before she did that, she processed a roll of film and took the film receipt and put it in the jag of Rob Pace's coat.
Hold on. So you sorted it, right? Sorted it, so nodes I is, that's the original position.
So now police have the proof and the evidence they
So
need
nodes
to get that
original
search warrant
position.
Gacy's house to examine that crawl space.
So maybe 6 hours, she talked continuously, describing every murder.
I did kill him. I think he was trying to help me.
She remembered every single detail.
Okay, I actually don't understand this part. That's a different problem. I think it's the same. The swap.
He finishes talking, and said just drop it. Start smoking.
We have the original position, yes. We know the original position, we know the current position. So you say you just grab the original position. How could you grab the original position? Because the original position is a different value.
Stands up.
Right? It's a different value. Because you already sorted it.
And I had a baseball bat around. I went over and I picked up this bat. And I hadn't walked that much.
Count swaps needed to match indices with original positions.
I had a zillion things going through my head, like, oh my god, what am I gonna do? It was frightening.
Okay, so
I just told us he killed all
we
these
just need to see
people. He's crazy.
the positions, right?
I was in a panic.
Oh, to go back to the original. Okay. So now let's say we have 5 and 0, so we need to swap 5 and 0.
On our job, we see
Right, you swap nodes I and then nodes this. So you swap them.
Victims of a man who probably did not know their names.
Right, you swap them. Because you swap, you know what should be at this position. Because current position is 0, but my position is this. So you go to this position, so you need to swap it. Right. After you swap it, you check again. So current position is 0. So you swap until 0 comes to the position. Ooh, this is actually a very interesting idea. I think we can do the same thing. I think we can do the same thing here. I'm not really that impressed by the idea. I think what I can do, I'll do this. I have vowels. I get their indices. Right? I got vowels, I get their indices. And then I'll sort them. So basically I can do something like this. like a pair. Right? Use the technique, the official solution, where we combine values and their original indices, sort them, and then count the number of steps to revert the sorted version back to its original. Right? So we do that, then we say we push back, should be know the value and your index, right? We don't need to do this, we need to do this. And after that, we can say vowels dot begin, and then vowels and dot end. And then we do this for this, right? For I equal to 0, we say if vowels I dot second is not equal to I, so we need swap. Right, so it's swap, RSTD. Right, swap vowels I and vowels I dot second. Right, we swap the two and then increment this and then check this position again, right? Because I swap this with this because it's not right, and I say, because this is a sorted version, right? So I say I need to, because its original position is this, but we need to swap back to 0, right? And just swap to the 0. So I say I'll swap whatever is there. I put myself, yeah. So this is putting this put vowels I to its right position, right? We put it into the right position. So I swap the two, so vowels I, current swap there, and whoever is at that position come in, can probably just swap again. Right, and the rest is the same. Right, I don't think the rest is any difference.
In the 70s, when a lot of teenage boys ran away.
So this is essentially the same solution as solution 1, except that we use the method in the official solution to count the number of swaps. Definitely, I don't think it's necessary to use the fancier version. Yep. Faster, huh? Okay, this one is done. Now we can go back to this. So this one is to find, basically, given two values, we need to find the smallest value. No, we'll find the leftmost value that's bigger than them. So my solution is I sort the queries based on the larger of the index, and everybody to the right of it will build a monotonic increasing deck, right, for it, and now binary search to find. I have the max of these two values, so binary search to find the first one, that's bigger than it, right? But then there's a little bit complication because we can land on it, so you have to have this extra special case. Like if you in the monotone increasing, you have the value that's exactly the same as your as the target, right? And then it depends on how we do it, right? How we do it. For example, if the two are the same, then you can go with. If the one on the right is on it and the one on the left is smaller, yeah, you can do it. But anything else, it's not gonna do it. So this is basically exactly how this is. So this is saying, right, if the target,
Yeah, it was a good side effect.
right, if the target is the bigger of the two queries, if the target is equal to because binary search is using upper bound, right? So it's equal to the previous one, right? Equal to the previous one. And then, if that's the case, then we have this special case, and we need to continue. So we have the possibility of they just stay in the same place, right? At least one of them don't move. So we say, if that's the case, then we need to have the current. This is the position, right? The position of of the value that's equal. It has to equal to the query, the bigger one of the query, which means on the right hand side, there's no need to move, right? And it has to be the left hand side height must be smaller than the current. So which means the left hand side, the one on the left, is able to move, or another one is if the position are the same. So there's like all these conditions, then we can use the current. Otherwise we do do whatever we need.
Judge, jury, executioner.
So it's monotonic stack.
Even now, my hair stands up on end, thinking, hearing those words, you say, oh, I tell you.
Which I think probably will be the same thing. Did they use any binary search or anything? I don't see a binary. Yeah, there's a search. There's a search. So you have to use a binary search. Of course, if you use this, you can tune it so it will give you yeah, you can basically avoid this type of hell.
You cruise around Chicago looking for young men to have sex with.
He
With
has just
such
enough charm to be able to pull up to the curb, roll the
such
window down, and say, "Hey, you looking for a job, or you want to take a ride?" Daisy took the
priority
ball
queue
in his
can
mouth
solve as well.
and had sex.
And the boy came into the bedroom with a knife in his hand.
For each index, we look for query pairs where both indices are smaller than, and for both values in the pair are smaller than the value.
Casey,
He went to the kitchen and he saw that
Max value index up to the current position.
the boy had been
So they pick the ones that's.
that's why he had the knife in his hand.
I see what it's trying to do, right? So you basically
Knife.
you will iterate through heights left to right, and for each one you will compare to the top of the heap.
This obviously was
And the top of the heap will guarantee two things. First, it's the minimum on the index, right? Minimum on the index, and so basically the minimum of the larger index, and
Oh, they're struggling to get a handle.
minimum of the larger index. Actually, I'm not sure. minimum of the large index, and then it have to be small, right? It has to be small. Now, which one do you prioritize? Is the minimum or the size?
Didn't bother him talking about it.
Okay, let's see.
6 hours went by with Gacy spilling his guts, going through his victims.
Jesus, a vector of a vector of a vector.
He had such a memory. He had just a.
Oh, because of priority queue.
Handling each victim,
It's greater.
how he killed them, what he did to them.
Your initial functional response about property. Quiero. People like you very
So A, B. If A is smaller than B, and height
I spend so much time.
A is smaller than height B, the result
Worse. As if they
query equal to
that's how he felt.
B.
Was phenomenal.
But the cops would soon discover for themselves just how deep this went. They started turning up to 4.
Else if A larger than B, this would be A. So this is the larger of the index. Right? Larger of the index. If A is equal to B, it'll be A.
Indicates suspicious with 15-year-old Robert Peete.
Else
He allegedly was last seen with Gacy.
They started turning up to 4.
it's A smaller than B, but height A is larger than. So A smaller than B, height A is larger than height B. Right? Just like one of them, one index is smaller than the other, but its height is bigger. So if that's the case, we get a maximum AB stored queries.
So it was at that time that I arrested John's murderer.
Stored queries. Store queries. Okay, store queries is a vector vector.
So that the search for more bodies can continue.
Right, store queries. Now pushback. Or pushback
John Casey had murdered
max of the height
I was so overwhelmed.
and its index.
I couldn't put it in words. I could not believe that a friend that I grew up with could end up doing such a terrible, terrible thing.
Well, you need a vector, vector, vector.
Back in the
That's a vector, right?
of the
Pushback, another vector.
we both went to the same school. Where Johnny and I met, we became
That's it.
best friends.
It's inside this. This is not a vector. This is a value, and this is another value.
Was incredible.
I don't understand.
Sisters loved Johnny very much. We had dreams and hopes like anybody would. We wanted to be the next good guy.
Right, so this vector is a vector.
John had a heart.
And in the vector you push back.
Father laid on him constantly.
Oh, we push back another vector. Wait, hold on. Oh. Oh, yeah. Okay.
Somehow explain how he got to be the way he is. If anything,
So the priority queue's minimum pair
relationship.
is less than a current. It is an answer.
History serves as
Okay, if the priority queue. So priority queue. Priority queue. Wait, where is priority queue? It didn't really get anything. Oh, you're putting. What is this? Top 0 smaller than height index. Height index. If the priority queue's minimum pair value is less than the current index of height, it is an answer to the query.
Be present. Or Mr. Gacy. Jan, you're so damn stupid and dumb.
Hold on, I don't quite understand.
I am smart. No, you're not. You got
Well,
yourself a
max index top 0 element. So it's the height, right? Height and its position, right? Height is its position. So we say heights. So for the queries we just get mm, bigger index, right? Query, I have the bigger index. Okay. Queries get a bigger index.
That affected Gacy. His psychological
And now we go through them one by one.
was to try to please his dad.
Oh, because if it's a bigger, you don't have to handle it. Ah, okay, that is something I did not consider. I didn't even consider that situation. Oh wow, okay. So the only thing you need to consider is if one is bigger, the other one is smaller. Right. Okay, so in this case, you push into the priority queue the height, right? The height. Okay. So in priority queue is height and its query index. And then you go through them one by one, and its height, its smallest height, right? The smallest height goes to the front, right? Smallest height goes to the front. And you go through them one by one, right? And for each height that you get out, if it's bigger or it's the top, this is smaller than current, then that is a result. That is true. Result, this, yeah, this is basically the index. It's equal to the current index, yes. And I will pop it. It means we have done this current. Yes, because we basically keep the inquiries with the smallest heights, right? Inquiries with the smallest heights. Inquiries with the smallest heights, right? Inquiries with the smallest heights. Then we say, if its height is smaller than the current, so we go from left to right for the heights. But what if the index itself
Was, I think, a major psychological blow to him.
I remember driving to his house, and there were so many cars there because this had leaked out.
It had turned into a circus, an amazing spectacle.
I don't understand. So this basically just says if it's,
His neighbors knew him as Johnny, the life of the party.
yeah, what if I index 0 is really big and the query is somewhere down the line,
And he realized he had to hide his feelings from
right?
everyone.
Query is something down the line, and then you will use the wrong index, and then you will pop the query out.
He knew his father hated
Pop the
homosexuals.
query out.
So John Wayne Gacy did what everyone did back then. He got married, he had 2 kids, and he kept his secret life a secret. He was living in Iowa.
And you go to that,
Kids, he
push the maximum index as the current index in the priority queue.
in our life.
Huh?
That he should be proud of what he's doing in his life. I think his dad might even have said, John, I was wrong about you. That was
I don't understand this part. It doesn't make any sense to me here.
he had sought his father's approval.
Like all we did so far, right? All we did so far is to push, right, the maximum height and the query index, right, into this,
Finally,
right, into this,
father's approval.
and
Something happened.
well, initially it's empty, right? It's empty. So
He was living a secret life.
yeah, because index 0 really cannot do anything. So you basically go to stored. So basically this is queries, right? Queries ending at this. Queries ending at this index.
And the boy goes to the police. And Gacy
right? Because yeah, queries ending at this index. So if a query ending at this index, you push them in. Okay, queries ending at this index, you push them in, right? So what can be guaranteed, right? What can be guaranteed is that every time when you push this into the priority queue, its bigger index is always smaller or equal to the index currently is.
So Gacy is charged with 3 other felonies.
Yes, because because when you push it in, you go through every index, right? And then the queue, priority queue is composed of all the queries whose indices are smaller or equal to the current one. So whenever you find any of them, right, with the smallest, smallest height, if it's smaller than the current, then this is the first height on the in the remainder that allows. So you can do this and you can, okay, yeah, that makes sense now. That makes sense now.
He was in prison for this horrendous charge.
Pretty smart.
Exactly what he had
Pretty smart. I think the whole logic can be made simpler. I think so. If we do a little bit change here, right? So we don't have to consider this situation. This situation will be handled here already.
1971, John, bought a house
Hmm.
just north of Chicago.
Priority queue is pretty strong
17 West
in this.
Central Avenue.
I don't know. Maybe I want to try this one more time.
Single-story homes, brick homes.
Yeah, maybe I'll try this one more time.
Working class.
Okay, that'll be it for today. I'll try.
Middle class,
I think I'll try the priority queue solution.
hardworking men and women.
I'll see you guys tomorrow.